The next sections in Chapter 11 deal with more reactions of alcohols, some of which we've seen before and some of which we're going to expand on reactions that we've talked about back in Chapter 7. So the first is dehydration reactions of alcohols are used to make alkenes, and that was back in Chapter 7 when we talked about making alkenes. So the dehydration reaction means that you're going to react an alcohol with sulfuric or phosphoric acid and heat, and you're going to lose H2O and form the double bond. Remember, the role of the sulfuric or phosphoric acid is that of a catalyst. And this is an equilibrium reaction, so it's sometimes difficult to get to push the equilibrium towards the right, towards the product, particularly considering that these are catalysts and actually not reactants. What we really should be writing is the alcohol and then over the arrows the H+, giving us our carbon-carbon double bond, and then our water. So adding more acid catalyst isn't going to push the equilibrium towards the right. So the way that we do this reaction in order to make the alkene in the highest possible yield is we take advantage of the difference in physical properties between alcohols and alkenes. Alkenes, being hydrocarbons, have low boiling points because they're only involved in dispersion forces. The alcohol is actually has a boiling point that's much higher because of hydrogen bonding. So oftentimes what's done is that they do the reaction at a temperature that's just below the boiling point of the alcohol, so that when the dehydration reaction occurs, the alkene boils off. So we might set up, for instance, a distillation apparatus that looks pretty crudely like this. And so what would then happen is we would then take our alkene, react it with the sulfuric acid, and alcohol react with the sulfuric acid. As the alkene then is formed, it would boil over, we'd collect it. Therefore, what I'm doing is removing the product as it's formed and using Le Chatelier's principle then to push the equilibrium towards the right. Now, remember that when we're doing dehydration reactions, that we always get the most stable alkene. And the way that we know what alkene we're forming is that we look at the carbon attached to the OH group as the alpha carbon. We look at all of our possible beta carbons, and then we would lose a beta hydrogen and the OH to form the double bond between the alpha and the beta carbons. The mechanisms of dehydration are going to vary from E1 to E2. If you have a secondary or tertiary alcohol, you're going to protonate it with acid. You're going to form the oxonium ion then. If this is a secondary or tertiary carbon, you'll then lose the water to form the carbocation and then lose a beta hydrogen to form the double bond. If you have a primary alcohol, the reaction is going to go by E2, so that you protonate in the first step, you still protonate the OH to make the oxonium ion, but it now cannot leave. And so in this case, we will either get loss of the hydrogen directly, and then kicking off the water to form the double bond. We can also get this reaction to occur. We can get rearrangements to occur in dehydration reactions. So the idea is that this is a one-step mechanism to form the double bond, and so this is the rate determining step, and in essence it doesn't involve a carbocation, which is why we call it E2, and E2 should probably be in quotes here. So secondary tertiaries undergo E1, primaries undergo quote-unquote E2. Now, going back to the last lecture, if we have alcohols, it's very easy to form the most stable double bond. That's the Zaitsev product, and so we would simply use phosphoric or sulfuric acid and heat, and that would certainly lose water, and we would form the more substituted double bond. But going back to the last lecture, we learned how to make the least substituted double bond, and to do that, we would need to react this alcohol with our tosyl chloride, and that would form then the tosylate ester. And then we would use, in this case, to form this double bond, I would use potassium tertiary in order to remove the beta hydrogen that's least sterically hindered. That would come in, remove that hydrogen, that pair of electrons, then would move to form the double bond, and we would kick the tosylate group off to form the double bond. So we do have ways to make either the more or less substituted double bond, but in dehydration, we're always going to form the Zaitsev product, which is the more stable, more substituted double bond. Now, one of the problems that we get into, in particular, I'll just talk about primary alcohols, is there's a side reaction that can occur when you try and take a primary alcohol and do dehydration on it. And let's say that we had butyl alcohol and I was trying to do a dehydration reaction using sulfuric acid and heat. Well, a side reaction is the one that can form the ether. So what I would do in my first step of the mechanism is I would simply protonate the OH to make the oxonium ion. And we could have a rearrangement occur where this secondary hydrogen would move over and kick off the water. But in this case, what's also likely to happen is that, well, actually that wouldn't be a rearrangement, that would just simply form the double bond. So we could have, in this case, just showing you what we'd like to happen if we'd want to do a dehydration reaction, is we would want this hydrogen to move here to form the double bond and then kick the water off to give us then our 1-butene. But what can happen with this carbocation is a side reaction where we could have that oxonium ion actually, particularly in the presence of a high heat, is we could have a second water, or we could have a second alcohol molecule come in and act as a nucleophile and attack the carbon and then have the water leave. So we could end up doing an SN2 reaction and actually then form, we would end up with this oxonium ion, and then we would lose the H plus to give us butyl ether. And so in order to do the dehydration of a primary alcohol, you do have an issue of trying to heat the reaction to get the dehydration to go, but then potentially having the SN2 reaction occur and give us the ether. And you might say, but wait, you said that like a halide wouldn't halides would come in and displace this, but how likely is a neutral nucleophile to come in and displace the water? Not really likely at room temperature, but again, if you're heating the solution to get the reaction to go, this is a possible side product. As a matter of fact, for those of you that took lab last semester or in the spring, this was a side reaction that we got when we reacted butanol with sulfuric acid and sodium bromide. the two side products that we got were the dehydration to form the alkene, and then the formation of the SN2 product, the dibutyl ether. We'll talk more about the formation of ethers from alcohols in the next chapter when we take up ethers as its own functional group. Okay, the next reaction that we're going to look at are some kind of unique reactions of diols. And one of the most unique reactions of diols is what's called the Pinacol Rearrangement. Now, Pinacol is this molecule with 2 carbons with OHs and then 4 methyl groups around that. When this reaction is heated in the presence of acid, it turns out that we get the formation of this ketone, which its common name is called pinacolone. And this reaction is really kind of different because we would not have predicted this product to be the major product of this reaction. And so this mechanism is interesting, and it also gives us a chance to see a lot of different aspects that are partially review and a couple of new things. So what is the mechanism of this Pinacol rearrangement? Well, the Pinacol rearrangement starts with the idea that I'm going to take the Pinacol and I'm going to react one of the OH groups with acid. And so what I'm going to do is I'm going to simply protonate the right-hand OH group with the acid. Now that's an equilibrium reaction because we know that the H plus could come off of that. So I'm going to get the formation of this carbon with the oxonium ion. And what do you think happens next when I form this oxonium ion? If you said it would leave, you're correct. So what's going to happen is I'm going to break that carbon-oxygen bond, and I'm going to end up forming this tertiary carbocation, which is pretty stable. So this part of the mechanism is pretty straightforward. We've seen this in basically in our SN1 mechanism of replacing OH groups with halogens, or even in dehydration steps. But now what happens is the following. We get a 1,2 methyl shift. So one of the methyl groups over here shifts over and then that forms this carbocation. So you might say, well, does that really occur? Because when I talked about carbocation rearrangements last semester, we always said that the driving force for this was the formation of a more stable carbocation. How does this work if I go from a tertiary carbocation to what appears to be just a secondary carbocation? Well, this isn't just a secondary carbocation. This is a carbocation that's next to an oxygen. And so what can happen is that you can take a pair of electrons off of this oxygen and move it there and write a second resonance structure. And once you write the second resonance structure, you could then imagine just simply regenerating the catalyst here, losing H plus, to then form the final product, which is the ketone. And so this is the mechanism of that Pinacol rearrangement, but still, why does this methyl group shift over? That would imply that this carbocation then turns out to be more stable than a tertiary carbocation. And it turns out that the reason for that is you form more than one resonance structures. The more resonance structures you can draw, the more stable the molecule is. And so these two carbocations are more stable than a tertiary carbocation. Also, part of the driving force for this reaction is the formation of, again, a very stable CO double bond. And so that is the driving force for this Pinacol rearrangement. So we see lots of different mechanisms here. We see the aspects of methyl shifts. We also see the formation of carbocations and a carbocation that actually has resonance structures to oxygen, which it turns out to be a fairly important reaction. So that's why the Pinacol rearrangement actually occurs. So another series of similar reactions that have mechanisms that are somewhat related to the Pinacol, at least in terms of having some alkyl group rearrangements, occurs with alcohols as well as double bonds. And these can be ring closures or ring expansion, and as we're going to look in this case, and rearrangements. So let's take, for instance, this example. And if we react this molecule with H+, what can happen is that we can actually get the formation of a 5-membered ring with the double bond there. This mechanism could also occur with a primary alcohol here, but I'll do it with this double bond to begin with. So this is an example of what's called ring expansion. If you take the double bond and you protonate according to Markovnikov's rule, what you'll end up with is we form the carbon-hydrogen bond and we form the secondary carbocation. Now, because this is a 4-membered ring that has a lot of ring strain to it, we have 90-degree bond angles here when we'd like 109.5. We can actually have a 1-2 alkyl shift, which will occur if we break this carbon-carbon bond and give it to that carbocation. So what I'm going to do is I'm going to do an alkyl shift, but I'm going to do that in the context of expanding or opening up the ring. Now, if I look at the carbons here, here's this carbon, here's a carbon that I'm going to circle, and it has 2 hydrogens. And then here is a carbon that has a square. And so what will happen is that this carbon, which I'm going to draw in bold, this carbon-carbon bond breaks, that pair of electrons moves to that carbon. So I end up with a 5-membered ring first. Now the carbon that became part of the 5-membered ring is the bold carbon. It has a hydrogen attached to it. The carbon that's circled here is now going to be the carbon that just formed that bond, and it has 2 hydrogens attached to it. Whereas the square carbon, in breaking this bond, that square carbon is here and it just has a single hydrogen, and so therefore it gets the positive charge. And then over here we have, this is a CH3 group, so I'm just going to go ahead and write that as CH3. So we form this secondary carbocation, but it turns out that because of the alleviation of this ring strain, we form a more stable carbocation. So having a secondary carbocation with ring strain is easier. It's much more stable to have a secondary carbocation on a 5-membered ring. And then in the final step of this mechanism, we're going to lose that H+, and we're going to generate our most substituted alkene. So we can end up basically doing ring expansion, and ring expansion will sometimes it'll oftentimes happen with a 4-membered ring going to a 5-membered ring. It can happen with a 5-membered ring going into a 6-membered ring, and sometimes we'll end up with ring contraction where we might go from a 7-membered ring down to a 6-membered ring. And your book has many examples of those, and we may do a couple of those in class as well as for homework. So that's a kind of a unique reaction. Now, even though this isn't an alcohol, could you write a similar mechanism for reacting this primary alcohol with H plus, to form that same product, only we want to start with not the 5-membered ring, but we want to start with the 4-membered ring. So could you write a mechanism that's very similar to this for that reaction? And you might want to try that, and we'll go ahead and we'll do that one in class. So the mechanism is very similar. It's just starting with an alcohol, and we would get the same product. Okay. Another reaction of an alcohol is esterification. An ester can be thought of as being made up of 2 parts. One part comes from a carboxylic acid, and the other part comes from an alcohol. And we'll talk about esters as functional groups much later on in the semester. But when you actually name an ester, like a simple ester to name would be this one, which is fairly common. This is ethyl acetate. We've used this in lab. The way that we name esters is we name the alkyl group from the alcohol part first, which in this case would be the ethyl, and then we name the carboxylic acid part with an ATE suffix, and so the 2-carbon acid is acetic acid, and so this is ethyl acetate. And we've seen in the in one of the previous lectures that this can be abbreviated as an acetate group because it is. So esters can be thought of as carboxylic acid part and an alcohol part. That's basically because Fischer esterification is one of the best methods to make esters, and what we do is we take our carboxylic acid and we react it with an alcohol, and I'm going to use just generic R groups and then R prime to indicate that they might be different. This is an equilibrium reaction. If we add acid to this as the catalyst, which we absolutely need to do, we'll end up forming our ester and then H2O. So we end up losing then an H2O molecule. And this is sometimes called a condensation reaction as well, since it produces water as the product. So Fischer esterification is fairly straightforward. You do need an acid catalyst for this reaction, but the big disadvantage of Fischer esterification is that it's an equilibrium reaction. And so in order to push the equilibrium to the right and form our ester product, we need to use an excess of one of these 2 reagents. And typically we use an excess of the carboxylic acid because in the reaction, we would then remove the carboxylic acid from the final product by simply reacting or extracting it out with sodium bicarbonate, because the bicarbonate would deprotonate the carboxylic acid, turning it into an ionic compound, which then goes into the water layer. So it's easy to remove the carboxylic acid by deprotonation. And extraction, it's very difficult to remove the alcohol. So typically we use excess carboxylic acid. I believe in lab that you will do a Fischer esterification and you will use an excess of the carboxylic acid to push the equilibrium to the right. And then you'll actually have to identify the unknown ester in that reaction. So the problem here is equilibrium. So even though this reaction works, it does have a little bit of an issue in terms of trying to push the equilibrium. We'll get into the mechanism of this reaction much later, but another alternative method to forming esters is to substitute the acid with a carboxylic acid chloride, and then react the carboxylic acid chloride with the alcohol. And what you end up doing is you end up forming the ester, and this is a complete reaction, so there's no equilibrium here. So the advantage here is that once we convert the alcohol or the carboxylic acid to the acid chloride, it pretty much is a straightforward reaction. We don't have to worry about equilibrium. We don't have to worry about having an excess of one or more reagents. We can just simply use the reaction like that. Now, how would you convert a carboxylic acid into a carboxylic acid chloride? Well, here's a review from the last lecture. Do you have a reagent yet in mind? If you don't, here's a hint. I want to convert an OH to a Cl. Not a very good hint? Well, can't use HCl. So how else can I convert an OH to a Cl? How about SOCl2 or PCl3 or PCl5? So you can actually make any carboxylic acid chloride you want by simply reacting the carboxylic acid with thionyl chloride or phosphorus tri or phosphorus pentachloride. So this is actually, if you're going for pure yield, this is the best method. But if you're going to go for sort of the ease of reaction, even if you're going to have to use an excess of the reagent, Fischer esterification is traditionally done with acid, alcohol, and then sulfuric acid or phosphoric acid as a catalyst. We'll get into the mechanisms of these reactions later on in the semester. Okay. The last topic is going to be forming other esters of sulfate, nitrate, and phosphate. So if you look at sulfate, if you take an alcohol and you react it with sulfuric acid, and if we write the structure of H2SO4, it's not going to be that. H2SO4 looks like this. And so one of the things you could say is, well, couldn't we just very easily take and lose water here to then give us our sulfate ester? And then couldn't we do that again with the reaction of, let's say, another equivalent of alcohol, so that we could lose another molecule of water to then give us the sulfate. And so we can actually do that, and we can form sulfate compounds. One of the kind of advantages of forming sulfate esters might be that if you wanted to then take a nucleophile and react it, it would come in and react with one of the alkyl groups. And again, we would do substitution, and the leaving group would be our resonance stabilized sulfate ion, similar to the tosylate esters that we talked about in the last lecture. So we can make sulfate esters, and we can make dialkyl sulfates by reacting sulfuric acid and an alcohol, and probably not heat, not a lot of heat, to form, because we don't want to form double bonds. We don't want to do eliminations. You can also form nitrate esters, and that's going to require taking an alcohol and reacting it with nitric acid, and nitric acid would have here's one of the two resonance structures for that nitrate. And so if we wanted to form, for instance, the nitrate ester, we would simply have our alcohol come in, and we would lose water again in a condensation reaction, and that would then give us the formation of this nitrate ester. Now, one of the issues with nitrate esters is that if you make a nitrate ester, in essence you have a nitrogen dioxide molecule embedded within here. So this molecule could actually sort of decompose, and you would form the NO2 as your product, and that would create all sorts of issues, because the problem with NO2 is nitrogen dioxide is it's a gas, and so if this is a liquid or a solid and you form a gas, there's an incredible expansion going from solid to gas. And if this is an exothermic reaction, then that heat is going to expand that gas even farther, and you have problems. Namely, you have an explosion. And so nitrate esters make very good explosives. Now, don't send the FBI after me, because if you're stupid enough to do this, then, well, I guess there would be some justice in that. But here's the most famous example of forming a nitrate ester. And that is to take this molecule called glycerol and react it with 3 moles of nitrate, or of nitric acid, to form then, and I'm just going to write the NO2 group as an NO2, to form trinitro glycerin. Well, we know trinitroglycerin without the tri term as just nitroglycerin. Okay? And if you were dumb enough to make this, you would find out that if you make nitroglycerin, it tends to explode when it's shocked or heated. So about the time you went to pick the beaker up off the bench top, you would be, well, do that with the hand you don't write with, because that hand's probably going to have some issues. But the person who made nitroglycerin famous was Alfred Nobel. And Alfred Nobel founded a company that made nitroglycerin in Sweden, the, I believe, Dynamite Nobel Company. And they had all sorts of issues preparing nitroglycerin and transporting it because it would tend to explode, and in making it, occasionally people would die from the explosions, including some of the people in Nobel's family. And just as a sort of an aside, it turns out that Alfred Nobel is a Swedish chemist. He is like the sixth cousin X numbers of removed from one of my great grandfathers. So in theory, Alfred Nobel is some long lost relative of my family. None of the money made it across the Atlantic to the United States, but Nobel, actually half of Sweden is probably related to Nobel, is what most people calculate. But anyway, Nobel turned glycerin into nitroglycerin, and then what he found was that if he put this in diatomaceous earth, which that's sealite that we used last semester in lab, that when you put that into the diatomaceous earth, that it was much more difficult to detonate, but still could be detonated. He made them into sticks, and hence dynamite was made. And the name Dynamite Nobel is still the company that Nobel founded. The story goes, or at least the legend goes, that at the end of his life, he donated the money to form the Nobel Prizes, as sort of because he was, feeling bad about some of his relatives being blown up in this process. And so that's where the Nobel Prize originated. You can actually do this demonstration. Dr. Wayner will do this occasionally. Maybe I will do it in class when we talk about this. But you can actually take cellulose. So cellulose is just basically cotton. And you can nitrate all of these OH groups by treating a cotton ball with HNO3, and you form what's called nitrocellulose. Nitrocellulose then turns out to be extremely flammable, and nitrocellulose are used, we use them as filters for filtering out bacteria, membrane filters that are used that are like 0.45 microns. Those are made of nitrocellulose. If you take a cotton ball and do this reaction, then you can actually take the piece of cotton, and using the flame, it's quite spectacular. But in the old days, film, yes, film, like in big reels, was made of nitrocellulose. And so one of the issues when people store large quantities of film is that it turns out to be it's exceptionally flammable. And so, in the Hollywood vaults where all of the old films are stored, they have take great precautions to make sure that it doesn't catch on fire, because nitrocellulose is very good. It burns very easily. It's not explosive like nitroglycerin, but it does burn very, very, very easily. Okay. Phosphate esters, last topic. So phosphate ester would be if you took an alcohol, or if you took a dialcohol and you were to react that with the phosphate, with phosphoric acid. Your phosphoric acid, if you remove the two hydrogens from that, if you remove two of the hydrogens from that, you can actually make the phosphate ion. And so you can form then, you could very easily form phosphate esters, or you could take a phosphate group, and it could be attached to two oxygens that are attached to two other groups. And these phosphate esters, that's DNA. So when you have your ATCG base pairs that are attached to rings with CH2s, it's this P, this little phosphate group, that is linking all of those base pairs, or linking all the sugars together that the base pairs are hanging off of. And so phosphate esters turn out to be very important in biochemistry, and you'll talk about those in DNA structure when you go and take biochemistry or genetics or one of the biology or biochemistry courses. Okay, so we can form sulfate, nitrate, and phosphate esters. We're not going to use those very much in organic, but it does turn out that the other ones do have important uses, particularly the phosphate esters, when it comes to biochemistry. So, what have we seen for today? Dehydration is a reaction we talked about last semester. You react an alcohol with sulfuric phosphoric acid and heat. If it's a secondary or tertiary alcohol, you go by an E1 mechanism, and you'll form the most substituted double bond. If you use a primary alcohol, you will go through a mechanism that does not involve a carbocation, and so therefore you can actually only form one double bond because there is only one alpha carbon and there's only one beta carbon in a primary alcohol. So you're pretty limited. Now, if you have rearrangements occur, then you can get other alkene products. We can form ethers as a side reaction from alcohols, from dehydration reactions. In this case, we have once we form our primary, or our oxoniamine attached to the primary carbon, we have the alcohol then attack and do an SN2 reaction. Again, this occurs at elevated temperatures to form the ether as a side product. The Pinacol rearrangement is a unique reaction of a dialcohol. It involves the formation of a carbocation, a loss of water to form a tertiary carbocation, a methyl shift to give us a carbocation attached to an oxygen, which then has two resonance structures, so it turns out to be more stable, and then loss of H plus gives us the ketone. We also have reactions where we can end up with ring expansion, and the ring expansion can occur by having a 1,2 alkyl shift from one alkyl group to the carbocation. This will occur to form a more stable ring, such as going from a 4-membered ring to a 5-membered ring, going from a 5-membered ring to a 6-membered ring, and sometimes actually contraction going from a 7-membered ring down to a 6-membered ring. This can occur with alcohols. If you protonate this alcohol, do a 1,2 methyl shift, and then the steps that are shown up there. Esterification occurs when you take an alcohol and react it with a carboxylic acid with an acid catalyst. That's Fischer esterification. This is an equilibrium reaction with the disadvantage that you have to push the equilibrium towards the formation of the products, which means you have to use an excess of one of the reagents, typically the carboxylic acid. And we can form what are called inorganic esters, the formation of sulfate, nitrate, and phosphate esters by using sulfuric acid to form either a alkyl sulfate or a dialkyl sulfate. We can form the nitrate esters by reacting nitric acid with an alcohol to form nitrate esters, the most famous of which is nitroglycerin, which made Alfred Nobel his fortune, and lost a couple family members along the way. We can nitrate cellulose to make nitrocellulose that we use in filters, and it's used in the old-time movies. And then finally, phosphate esters can also be formed, and phosphate esters turn out to be very important in biochemistry. And in particular, they link the sugars that hold the base pairs together in DNA. Okay. There will be an online quiz on this, and then if you have any questions, bring them again to class, and we'll do some reactions and answer any of those questions that you have.